Modern enterprise networks are sprawling ecosystems. Between cloud infrastructure and endpoint software, they continuously broadcast massive, chaotic streams of raw telemetry. Many security teams operate on a straightforward assumption. If they can collect all of this data, they will catch more threats. The immediate consequence of that assumption is financial. Routing every raw telemetry point directly into a monolithic SIEM creates a linear surge in ingestion costs relative to data volume. The technical consequence is even more severe. A SIEM's correlation engine requires intense compute power to analyze data. When flooded with low-signal routine events, that engine becomes computationally overwhelmed. And for the human analysts, the systemic output of an unfiltered SIEM is alert fatigue. They are forced to investigate thousands of false positives. This happens because teams conflate two different functions: storing raw evidence so it can be searched later, and processing high-value signals for real-time threat detection. Legacy SIEM models fail because they attempt to execute both deep storage and real-time analytics inside the same architectural layer. Without a routing strategy, increasing telemetry volume doesn't improve visibility. It degrades the Security Operations Center's ability to spot an actual attack in the noise. The engineering solution to this paradox is a decoupled security data pipeline. We separate the architecture into two distinct layers. On the left, we have log management. All high-volume data is diverted here for cost-effective retention. On the right is the SIEM. Only a heavily filtered, refined stream reaches this side, built for real-time threat analytics. Decoupling the architecture solves the cost and performance constraints. Raw evidence is stored where it is economically cheap, reserving expensive compute power for high-fidelity signals. Getting that clean, filtered stream into the SIEM requires heavy lifting in the pipeline. As raw telemetry arrives, it comes in vastly different formats from disconnected vendor ecosystems. A modern cloud infrastructure provider like AWS will send its audit trails formatted as nested JSON payloads. Meanwhile, an older network intrusion detection system might output its telemetry as legacy XML files. To fix this Babel problem, the pipeline executes normalization. Watch how disparate labels, source IP, source address, and IP origin collapse into a single schema field. The normalizer strips proprietary formatting, locking data into a uniform structure isolating core entities, source IP, destination, and timestamp. Without this structural alignment, a SIEM's correlation engine has no way to query across the two different data sources. It cannot read them at the same time. If you force unnormalized data into the SIEM, detection engineers must write highly complex search queries. Those queries are brittle, breaking when a vendor updates their logging format. Rigorous data normalization inside the pipeline is a strict prerequisite. Until the fields match, cross-platform threat correlation is impossible. Normalization has historically been a major friction point. The industry initially relied on standards like the Common Event Format, or CIF. But CIF was built around network-centric data, making it difficult to adapt to modern cloud and identity logs. Individual vendors responded by creating their own proprietary data models, like Splunk's CIM or Elastic's ECS. Adopting these models trapped organizations in vendor lock-in, making it difficult to change tools. To break this cycle, the industry is shifting toward OCSF, the Open Cybersecurity Schema Framework. It is a vendor-neutral, community-driven standard designed to handle the complexity of modern telemetry. Looking at the OCSF architecture, it divides data into two categories. On one axis, it defines static objects, like a user or device. On the other axis, it maps event classes, representing the specific activity happening to those objects over time. Adopting an open standard like OCSF decouples the data producers from the data brokers. It allows the Security Operations Center to own their data pipeline without being hostage to the schema of a single SIEM vendor. Even when data is perfectly normalized, it is flat. A clean IP address tells you nothing about whether a connection is malicious or benign. To solve this, the pipeline executes enrichment. This is the automated process of appending external context directly into the normalized log payload while it is in transit. First, the pipeline queries real-time threat intelligence feeds, flagging known malicious IPs before the data reaches the SIEM. Next, it injects geographic location data for those IPs and pulls in user context from Active Directory. This tackles the engineering complexity of identity resolution. tracking a single user as they move across changing network hostnames, dynamic IP addresses, and different endpoint agent IDs. Enrichment transforms a basic telemetry record into a fully contextualized package. It is finally ready for ingestion by the SIEM's correlation engine. Inside the SIEM sits the correlation engine. As uniform data blocks flow in, this layer calculates the dependent and independent relationships across those isolated streams. It operates using two primary logic models. The first is rule-based correlation. This relies on explicit threshold logic. For example, if the engine sees 10 failed login attempts within 60 seconds, it triggers an alert. The second model is statistical correlation. Instead of looking for a hard-coded threshold, the engine utilizes digital algorithms to observe the network and establish a normal behavioral baseline for specific users and devices. Under this model, the engine calculates the threat level of an anomaly by measuring how far it deviates from that established baseline. These baseline correlation models act as advanced noise filters. They automatically suppress routine network anomalies, allowing analysts to focus their attention exclusively on genuine behavioral deviations. The ultimate test of the engine is detecting advanced persistent threats, or APTs. Modern cyber attacks rarely occur as a single, loud security event. Attackers deliberately disguise their lateral movement. They break their intrusion into a series of discrete, seemingly unrelated, low-severity actions designed to fly under the radar. Catching this requires cross-correlation. This is the engine's ability to link those isolated events across different systems, network segments, and timeframes. Consider a hypothetical attack path. First, an alert fires on the email gateway, suspicious but non-critical. Hours later, an anomalous registry modification occurs on a local endpoint. Because the data is normalized and enriched, the engine draws a vector between them. Finally, a sudden cloud privilege escalation occurs, utilizing that endpoint's credentials. The connected path turns red, generating a single high-fidelity alert. The correlation engine identifies the high-probability relationship between these three events, linking them to a singular adversary executing a coordinated attack vector. But the engine can only perform that analysis if the data points match. The SIEM's ability to cross-correlate an APT and prevent a breach is entirely dictated by the structural integrity of the pipeline feeding it. You cannot correlate what you have not normalized.